Hi guys, sound check.
I can hear you.
Just in case, is there anyone who doesn't speak Russian? Okay.
Not
So
yet.
I believe again.
Not yet, I think.
Okay.
Yeah, I
But,
cannot see anyone.
so I mean, well, if you wish, we can switch to Russian. But вот, потому что раз все из присутствующих говорят по-русски, может быть, просто будет проще общаться.
Да-да-да.
Игорь, извини, цирка не будет. Вот. Oh, by the way, that guy, Jintao, does he speak Russian?
Hello. Yes, I can understand.
Oh, but I believe it's better if we stick to English. Am I right?
Not equally.
Okay, but I mean, it's okay if we speak English, but I just want to know if there are any problems.
Sorry, I can't hear.
Okay, then, like by default, let's stick with English. Okay, so the reason why we're here today is because you probably have some questions, or probably a lot of questions, and my task to answer to all these questions. So just tell me what you want me to explain, and we will go.
Okay, yeah. Before we start, like with the main part of the consultation, we've discussed on the lecture the possibility of switching from Examus to Zoom, and you asked me to come to the consultation to discuss it further. So we can probably start with that, just to.
Yeah. Okay. I see. Okay. Let me explain the situation.
Okay.
Well, there are two events. The first event is the test, which will be this Saturday, and then the exam. So regarding the tests, we switched to Zoom. So there was no problem to avoid using Examus, but there is a problem with the exam. Because, well, since we already have chosen Examus as the main platform, and since this is an exam, we cannot change our decision since the beginning of the May. So that was the decision of the university. So they don't want to change this decision. So since it's already chosen, we cannot switch the platform.
We actually had the same case at the linear algebra.
Okay.
There, I guess we managed to avoid using Examus at exam because, firstly, study office said that we should use Examus and we have no other choice. However, our lecturer and seminarists were against Examus, and we wrote like a big letter to the study office from the students. And they, from their side, also said to study office that they are against Examus. And as far as we've been told by our teachers on the linear algebra course, the study office agreed with us, and we will not use Examus. However, it's not the final information.
Well, I have a different information. The study office told me that they switched the system they will use. So the Examus will be used, but they will use a synchronous proctoring system instead of synchronous. So that's what I was told by Tatiana Pak, like yesterday.
Okay. We have to get some more information from them, I guess.
Okay. So if I know something new, I'll tell you, because I have exactly the same problem on the other courses where I want to avoid using Examus during the exam. So if something changes, I'll tell you.
Okay.
But currently, well, we don't use Examus this Saturday, but
Yeah.
well, by default, we will use it on the exam.
And one more question then regarding the test on Saturday. The first one is, will the students, how it will be conducted? So we enter the Zoom conference, then what?
Okay, so I'll send you all the instructions, like probably tomorrow or on Friday. Well, basically, you have to log in to Zoom. Well, there are some requirements to your nickname. There must be like the number for the group, then the surname, then the name. Then you must turn on your webcam. Then you must share your desk. How it's called?
Desktop, probably.
The screen. And you must share the screen.
But I mean, as far as I know, there is a limitation that only one person in the conference.
No, there is no such a limitation now. So there is an option to when everyone can share its own screen. So I will see all the screens here.
Okay, yeah.
Then I'll send you 3 links containing the information, well, containing the test itself, one link for each group. Well, you open the link, you write the solution on a sheet of paper or, well, using any other device as you wish, and then you just scan or make a photo of the solution and send it via email to me. So that's more or less how it will be done.
Can we use LaTeX for writing the solutions?
Well, you can, but I do not recommend doing that because it will eat a lot of your time. Because writing on paper is much easier. So
we have some people who want to, so I'm asking just for them.
Okay, if you wish, you can.
Okay.
But believe me, it will be much slower than.
Yeah, I understand that, but I mean they don't. I'll tell them, but I mean.
Okay, if they can draw pictures using TIX package, okay, then they will probably like solve 0.001% of the task.
Yeah. Okay. So okay, thank you. I'll talk to the study office and to linear algebra teachers to clarify what we have going there, because for now it's not really clear, and I'll maybe contact you with via email to further clarify the situation with the exam.
Okay, that would be nice, because I think am I right that Andrei Mazhuga is your lecturer?
Yes.
Okay, I'll write him, and probably Nikita Medved is.
Nikita Medved actually told us that there will be no exams after all this story that we wrote to the study office, and then Andrei Mikhailovich wrote to them too that he's against exams. But I mean, we didn't get the official announcement. It was only that Nikita Medved told on the seminar.
Okay, that's interesting because the official position was completely different.
Yeah.
Probably Tatiana doesn't want to do this process again.
Maybe.
Okay, I see. But that's a nice piece of information because that's really new to me. I thought, well, yesterday I literally discussed this problem with Tatiana yesterday, and I was told completely different information. So that's not how it looks like now. Okay.
Yeah, and it's just kind of confusing, but I guess.
Yeah, I'll discuss it with Nikita and Andrei also.
Yeah, so, thank you.
No problem. Okay, so are there any questions related to the algebra itself, or probably you want to discuss anything else? Okay, just to clarify, the reason why we're here today, because we have like the 11th lecture and the seminar, and there is no 11th week during this module. Well, because of many reasons. So it doesn't make sense to give you some new material because, well, we have already done a lot, and it's better to clarify the details that are unclear to you. So my goal for today is to answer two questions that you have regarding everything that we have already studied. So if you have any questions, so just feel free to ask them, no problem. So I can do it in like this. So to stimulate you if you're shying.
Well, I have one question.
Okay.
You ladies first.
Oh, okay. I'll be later. It was you first.
Okay, then I have a question. Like, for example, we have a polynomial x in power of 2y, and for example, y in power of 2x, and we have a lexicographical order xy. So, like,
Could you repeat the polynomials?
yeah, x squared y and y squared x.
Okay.
And we have lexicographical order xy.
Okay.
And it is obvious that x squared y is greater than y squared x.
Okay.
But we can't divide the first by the second,
Yeah.
or we can.
No, we cannot. That's the difference between the case of one variable. You can compare them, but the comparison is not based on the division. Only in some cases, you can divide a larger one by a smaller one, but not always. Well, actually, exactly the same problem happens here when you have a polynomial like this, x plus y. Then x is greater than y, but you cannot divide x by y. So you can draw all the monomials here on a plane like this. So this is the degree of x. So, and here you draw the degree of y. So the monomial here, let's say it's 1. The monomial here, I'm sorry, the monomial here is x, the monomial here is y, the monomial here is xy. So this table represents all the monomials. So if you take something like this is x squared y, because this corresponds to x squared, this corresponds to y. And then all the monomials divisible by this guy are these. So these are divisible by x squared y. And these monomials, they divide x squared y. So these guys, they divide x squared y. But if you look at this zone or at this zone, there is no division relation, because the division relation is just a partial order. So you cannot divide this guy by any of these ones or vice versa. But still, the lexicographical order is a linear order. You still can compare them. So yeah, that's a subtle difference between the case of one variable and the case of several variables. So more or less, the way how the lexicographical order was invented, or how we use it, is we want to make this division order, the ordering by division, we want to extend it to a linear order. And lexicographical order is just one way to extend the division order to the lexicographical order. There are a lot of other ways, but we don't use them. Okay, I hope that was the answer to the question.
Yeah, cool, I got it, thank you.
No problem.
So can I ask another?
Yep, no problem.
So it's a problem from our third homework, task 2, namely write down formulas for an isomorphism and its inverse in case Z6 times Z20 is isomorphic to Z10 x Z12.
Okay, how to write an isomorphism in this particular case. Okay.
Yes.
So, okay. First of all, you should use Chinese remainder theorem to do that. So let's see what happens here. First of all, the idea how it works, you should split each cyclic group on the left, each cyclic group on the right, and you will see that the result on the left-hand side and on the right-hand side will be the same. So let's see. First of all, so we still don't know how it works. So this is what we want to find. But on the left-hand side, at least, Z6 is a product of Z2 and Z3, okay?
Yeah.
Now, 20 is a product of 4 and 5. So Z20 is Z4 times Z5. So here I use the Chinese remainder theorem for the first and the second factor. Okay? So
Okay.
now let's do this for the factors on the right-hand side. So Z10 is a product of Z2 and Z5. And Z12 is a product of Z4 and Z3. Here again, each isomorphism here is just the Chinese remainder theorem. But now, as you can see, the result is exactly the same, but the factors are in a different order. So here, for example, Z2 and Z5 are here, and here Z2 and Z5 are here. And the same thing, Z3 and Z4, Z4 and Z3, okay? So now you can identify these guys. So you have an isomorphism which goes from this ring to this ring, then an isomorphism which goes to here, and then you have an isomorphism which goes here. So we just need to write down all the isomorphisms here and compute the composition. So let's do it. So first of all, we want to go from here to here. What do we have? What do we have here? We have a pair of elements, A, B, where A in Z6 and B in Z20. And how does this isomorphism works? Well, we take A to a pair AA, where and B to a pair BB. This is how the arrow from here to here works. So you should think of it like this. A was here in the 6, and it goes to A modular 2. Well, when I write this, I mean A modular 2 here. And when I write this, I mean A modular 3. And when you have B from here, it goes to B modular 4 here and B modular 5 here. Okay?
Okay.
Now you have to permute the factors. So the first factor is on the same place. The third factor goes to the last place. The fourth factor is on the same place, but the fourth factor goes to the second place. So you want to switch A and B here. So now it goes to A, B, B, A. Okay? And now you want to go back. You want to go here. You must have a pair of two elements. And how does it work? You apply a map to this pair and get an element here, and you apply some map to this pair and you get an element here. But what are these maps? So an isomorphism from Z10 to Z5 was a map from here to here, which takes an element to, well, let's say an element X to a pair XX, well, modular 2 and modular 5. And now we need to apply the inverse map to this particular map. And exactly the same here. You just apply the inverse map to the Chinese remainder isomorphism here. Okay, let me compute the inverse map here. So we have Z10. So it goes to Z2 times Z5. So when you apply it in this direction, it takes k to k modular 2 and k modular 5. But now we want to apply this in the opposite direction and find the corresponding remainder modular 10. Okay, you do it in 2 steps. First of all, you want to find the images for these guys. Okay, how do you do this? You take the elements 5 and 2 and compute their greatest common divisor and express the greatest common divisor as the linear combination of 5 and 2 with some integral coefficients. Well, we know that the greatest common divisor is 1, and well, steering at these numbers, we can know that 5 minus 2 times 2 equals 1. So the greatest common divisor is the combination of 5 and 2 with coefficient 1 and minus 2. Okay? And now, well, since this map is an isomorphism, so there is a unique remainder here which gives you 1 modular 2 and 0 modular 5. What is this number? Well, you may guess this number is just 5, but how do you get it from this equality in general? Well, let's move this summand to the left. Then we will get 1 plus 2 times 2 equals 5. So now, as you can see from the right, so these are the same numbers. So this is the number 5. But what are the properties of this number? Well, modular 5, it gives you 0 because of the right-hand side of this equality. Modular 2, it gives you 1 because of the left-hand side equality. So 5 is the number giving you 1 modular 2 and 0 modular 5. So if you want to solve the second problem here, you move another summand on the left, and you get 1 minus 5 equals minus 2 times 2. So again, this is exactly the same number, minus 4. And because of the right-hand side, it gives you 0 modular 2. And because of the left-hand side, it gives you 1 modular 5. So the number minus 4 is the one with required reminders modular 2 and 5. And if you wish, you can replace this minus 4 by 10 minus 4, which is 6, because 6 and minus 4 are exactly the same numbers here, but you may use any of these. Okay, so this solves this problem. This is an intermediate problem, but just in case, is it clear what I've done here?
So.
Okay, okay. So then I probably should, let me repeat and clarify what's going on here. So now I'm trying to solve a problem in this particular case. So we have this isomorphism between Z10 and Z2 times D5, okay?
Mm-hmm.
What does it mean that we have an isomorphism? We have a map in one direction and a map in the other direction, and these two maps are inverse to each other, okay?
Mm-hmm.
So the map in the left to right direction is always the same. It takes element k and it takes it to k modular 2, let me write it precisely, and k modular 5. This is how it works. For example, if you take 5 on the left-hand side, the 5 goes to 5 modular 2, which is 1, and 5 modular 5, which is 0. So, for example, element 1 goes to 1, 1, element 2 goes to 0, 2, element 3 goes to 1, 3, etc. Okay?
Mm-hmm.
This is how the isomorphism works from left to right. This is always how it works. There are no exceptions to this rule. So when you go from the left-hand side to the right-hand side, this is always how it should be done. And I have already used this isomorphism when I map Z6 to Z2 times D3. I map the element A to this pair A modular 2, A modular 3, okay? So, but here, when I want to go back, well, for example, on the right-hand side, exactly the same map is applicable when you go from Z10 to Z2 times Z5. You take any reminder here, let's say A, and it goes to A modular 2 and A modular 5 here. So this is how this direct map works from here to here. Now I want to describe the inverse map to this one, okay? So the general idea to find the inverse map is this. First of all, you want to find an image, the image of these the images of these two guys. So
And why have we chosen exactly 1, 0, 0, 1?
okay, you'll see in a minute. You'll see in a second. So let's say we know the answer for these guys. So these are the answers as I computed them. But then the element of the wrong color, the element AB can be presented as A times 1, 0 plus B times 0, 1.
It's like the basis, right?
Yeah, yeah.
Oh,
It's
okay.
like the and then if you know the image of this guy and the image of this guy, these are just natural numbers or integer numbers. So this multiplication by A means that you add this element A times. Or if A is negative, it means that you add this minus A times and then multiply by the minus 1. So if this guy, let's say this one goes to 5, and this one goes to minus 4, as I have computed, then the whole element goes to 5 times A minus 4 times B. So the inverse map, so the answer for this one will be 5A minus 4B. So that's why, so this is the reason why you want to compute the map in this particular case. Because when you know these guys, you know the answer for any pair AB. So now, is it clear how to, well, I mean, in general, how to produce a map from the right-hand side to the left-hand side? The general steps that you, and why I need them. So,
Yes,
okay,
but
so,
I have one question, like, so am I right that we are not, it is not important to calculate U and V, we just can solve the system of equations like x modulus 2 equals to 1 and x modulus 5 equal to 0 for 1 and 0.
Yeah, you don't have to compute this, but this is just a general way how to do this. You may guess these numbers. For example, in case of 2 and 5, it's clear which number should I take to get a remainder 1 modular 2 and remainder 0 modular 5. This simply means that I have to take an odd number divisible by 5. Just take 5. That's it. Well, so you may solve the equation if you wish, but so the equation means that you're looking for a number giving you this pair of reminders. You can go through all the elements of Z10 because there are only 10 elements, and you may compute precisely which one gives you exactly element 1, 0. Just go through all of them, and when you find the required element, that's your answer. There are a lot of ways how to compute the images of these two guys, but this one is just a general rule. So if you don't know how to compute, you may apply this rule and it always works. That's the reason why I explain this using the Euclidean division algorithm and greatest common divisor. But okay, I don't remember who was asking the question, but just in case, since that was the answer for you, please tell me, is it clear now how I compute the inverse map, or should I go through the algorithm once again?
No, it is clear, but that's only the isomorphism between Z10 and Z2 times Z5, right?
Okay, yeah, that's right. But
Mhm.
let me recall where we stopped. So we found that this first map here takes AB to 5A minus 4B. Now we should find the second one, this psi. Find psi. Yeah, that's how they should be called. So we should apply exactly the same technique to find the inverse map for these isomorphisms. So we consider Z12 to Z4 times Z3. So we consider Z12 to Z4 times Z3. Oops. Do I use the correct order? Yeah, I used exactly the same order. So the direct map takes K to K, comma K. So it's exactly the same. But in order to find the inverse map, I should find the images of these guys. So what are they? Again, I can take the element 4 here, because 4 gives you 0 modular 4 and 1 modular 3. That's not a problem. And then I should take minus 3 here, because minus 3 gives you 0 modular 3 and gives you 1 modular 4. Okay, this simply means that the general map is given by the rule minus 3a plus 4b. Now, is it clear?
Yes.
Is there anyone who doesn't understand what's going on here? Okay, but just in case, even if you think that you should understand what's going on here by now and do not understand, it's better to ask a question, because I can, if it's needed, I can repeat everything like 10 times, 1,000 times, it doesn't matter. The only thing that, yeah.
We haven't found the inverse isomorphism yet, right?
Yeah, we're on the way. We're
Okay,
on the way.
thank you.
So, and here you see I use A and B, and I have to apply these to a pair B and A. So I will switch the letters, and here we have minus A plus 4B. So I will write there minus 3B plus 4A. So minus 3B minus 3B plus 4A. So let me show you what's happening here. So I started here with a pair of elements A and B, A from here, B from here. Then this pair of elements goes to a quadruple of elements, like here, by the rule AA, BB, because this is how I apply an isomorphism from here to here, and then an isomorphism from here to here. Then I compare the left-hand side and the right-hand side, and I see that I have to change the order of the elements. I will change the second and the fourth one. So I change them, and this element goes here to ABBA. And now I should apply to this. So this pair lives here, and this product is isomorphic to this group. So when I go from bottom to up, I should map this pair to the corresponding element in Z2, in Z10. So I have to apply this map from Z2 times Z5 to Z10 to this pair, and this will give me one element here. And then these guys go here, and exactly the same, this pair lives here, and when I go up, this pair must go to an element here, and this is done by this rule. So at the end, when I go from here, 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 and here, the composition looks like this. The pair AB goes here, and then here. Well, I just rewrote this pair here because I have some place here to write the formula. So the composition works like this. I take the pair AB, and this pair goes to this pair of elements here. So if I take A from here, B from here, then the result will be 5A minus 4B from here, and minus 3B plus 4A from here. So this is how the map is produced in one direction. So now we have the isomorphism from the left-hand side to the right-hand side. Are there any questions regarding this procedure?
No?
So now it's clear, okay?
Yes.
Okay, that's cool. And if you want to find the inverse map, you just repeat all this procedure, but in the opposite direction. So you start with the pair AB from this guy, you map it to a pair AA, comma BB in here, then you map it here. Also, you switch the second and the fourth element, and then you go up on the left-hand side. So you apply to a pair AB the inverse to this isomorphism, and to the pair BA the inverse to the isomorphism between Z20 and Z4 times Z5. And this will give you the inverse map. And that's it. So should I repeat the inverse map? Or should I compute the inverse map?
No, I think it's clear now. Thank you.
Okay, no problem. But just in case, you know, well, if you wish, I could do this. No problem. Okay. Are there any questions related to this particular problem? Okay. Are there any other questions? Could you explain one more time why Zn? Oh, okay. There was a question in the chat. Why do you always have this Chinese, this isomorphism in the Chinese remainder theorem? So let me show you. So in general, suppose you have Zn times m, and we produce this map from the left-hand side to the right-hand side, and the map is given by the rule k goes to k modular n, k modular m. And we also, by the way, let me put a line here. So, and we have that the greatest common divisor of n and m is 1. So I want to show that this map is an isomorphism. Okay. So let me denote the map by phi. So first of all, we should know that phi is a homomorphism. Well, of what? Of groups. Well, it's actually a homomorphism of rings. Well, here we have addition, and here we also have a coordinate-wise addition. And with respect to this operation, phi is a homomorphism. Well, but actually we have a multiplication here, a multiplication here, a multiplication here. So multiplication, coordinate-wise multiplication on the right-hand side, and phi actually preserves the multiplication too. So this will be so the left-hand side also, we may consider the left-hand side and the right-hand side as a ring, then phi is a homomorphism of the rings. But just for now, let's think that the left-hand side and the right-hand side are provided with the addition operation. So we just forget the multiplication, and phi preserves the addition. Well, why? Well, this is simply because, well, if you look at the map, this is how the map is defined. Just by definition of the map, phi preserves the addition. Well, but just in case, are there any questions why this map preserves the addition? Why it's a homomorphism of groups? Okay, that's good. The second thing, let's compute the kernel of this homomorphism. What is the kernel? The kernel consists of all elements going to 0. This is just by definition. But now let's recall the explicitly the definition of phi, which means that k mod n equals 0 and k mod m equals 0. So we're looking for all k's with this property. But again, just reformulate this one more time. This means that n must divide k and m must divide k. So we're looking for all k where in z n times m. Let me write it here for clarity. So we're looking for k here. So it's a number from 0 to n times m minus 1. And now we're looking for the numbers k with these properties. So n must divide k and m must divide k. But now we use that m and n are coprime. In this case, this implies that the product must divide k. But k was the number between 0 and m times n minus 1. So here we have strict inequality on the right-hand side. And it's divisible but by m times n. So the only option is that k equals 0. So the only option we have is k equals 0. So that's why the kernel consists of the 0 element only. So the kernel consists of the 0 element only. Alexander, is it clear? Okay, but what does it mean that the kernel is 0? Let me recall you that a homomorphism of groups is injective if and only if the kernel consists of the neutral element. Yeah, you're right. This is, I see that you understand what's going on here. So phi is an injective map from here to here. But now, just if you compute the amount of elements on the left-hand side, you will get n times m elements. And if you compute the amount of elements on the right-hand side, you will get exactly the same number. So this is an injective map between two sets of this with the same amount of elements. So it must be surjective because there are exactly the same number of elements. So the surjectivity is automatic. So phi is surjective automatically. Yeah. So there is a trick here. So you don't check directly that it's surjective, but you can do this explicitly. So when we find the inverse map from the right-hand side to the left-hand side, we actually find an image for a given pair of elements. And how it's done in general, so since 1 is the greatest common divisor of n and m, we present it in the form u times m plus v times n. And that trick, oh yeah, I'll share these notes with you. Do you mean the whiteboard? Oleg? Yeah, yeah, it will be uploaded. So when you use this expression for the greatest common divisor and do this trick, like moving this element to the left-hand side, then it simply means that you find an element u times m, which is equal to 1 minus v times n, and this element goes to, I forgot your n was first, and it goes to 1 times 0, and the element v times n, which is equal to 1 minus u times m, it goes to 0, 1. So these expressions, they solve the problem for these particular elements. And now, since you know these guys, the element a u m plus b v n goes to a b. So when I find, so the problem of finding the inverse map for this particular isomorphism, well, is actually, I'm sorry, just let me say it again. So the problem of finding the inverse map for this isomorphism is equivalent to computing a preimage of any pair on the right-hand side. So the way I computed an image of a given pair, you see, is exactly the same method I used to produce the inverse map. Because, well, in this case, since this is a bijection, so finding the inverse map coincides with finding a preimage for a given pair on the right-hand side. No problem for interrupting me. So if you have questions, just feel free to ask them in chat. So when I see them, I'll try to answer them. No problem. so this must cover everything related to this isomorphism. So if you still have any questions, just go. Okay, are there any other questions regarding this? Okay, so are there any other questions in general?
I have a question, but I've already asked one, so maybe if no one else wants to ask, I can ask again.
Okay, if everyone is shy, just ask another question, no problem.
Oh, okay. I'll type it in the chat, like in 1 second.
No problem. Okay, find a generator for the field F25, for the multiplicative group of the field F25. Okay, so let me show you how it's done. So we have the field F25, and well, there are a lot of ways to produce the field, but we use a specific one where this field is given by the equality. So it must be quotient ring of Z5x by the polynomial x squared plus 2. Okay, and now, there was an item in the problem saying you must show that the element x is not a generator of the group F25 star. So yeah, so let me repeat. So we have this field F25, which is given by this expression. This is the quotient ring, the ring of reminders, modulo x squared plus 2. And we have the set of all non-zero elements here. It's denoted by F25 star. This is a group with respect to multiplication, and it's always cyclic. So it's a group Z24. Okay. So, so first of all, you should show the first step of the problem was to show that X is not a generator.
Yeah, I've proved it, but I have troubles with finding the generator.
Yeah. So now, and the second step was find a generator.
Yeah, but I have problems with the second step.
Okay, so let me show you how it should be done. Well, actually, there are a lot of guessing in this second step, but before doing some guessing, well, suppose that you are given an element of this field. Well, let's say I'll give you an element 1 minus x. How to check if it's a generator? Okay, so this is an interesting question. So, but now, well, this is an element of the group Z25 star, which is actually group Z24. So the first question you should ask is how to check if an element is a generator of Z24. Okay. Well, the element, let's say, suppose you have a group of with 24 elements. How to check? Well, and you know it might be a cyclic group. So how to check that some element G is a generator?
So its order must be equal to 24.
Well, order of any element is 24. So if you take any element, even the identity element. Oh, yeah. Oh, you're right. I'm sorry. Its order must be the 24. But how to check? Yeah, I mean, it's true that any element to the 24th power is the identity element. But yeah, in this case, this must be the smallest power that taking G to the identity element. But how to check that the order of G is 24? Well, let's split 24 into prime factors. Well, what would it be? 2 to the power of 3 times 3. Am I right? 8 times 3, 24. Yeah. So in general, there is a rule how how you check this. So the order of G is 24 if and only if you take this. For there are two prime factors, 2 and 3. You should raise G to the power 24 over 2 and 24 over 3. So here you go through all the prime factors of this number, and you must check that the result is not 1 in all cases. This is the criterion for an element being a generator in a cyclic group. I'll tell you in a minute why, but just in case, is it clear what should I check? What are we checking?
Yes, yes.
Okay, so in general, if your order is a more complicated number, for example, it's a product of 2 in some power, of 3 in some power, and 5 in some power. Let's say you have 2, 3, and 5 as prime factors here. Then you will have to check 3 conditions. You divide your order by 2, by 3, and by 5. But here we just have 2 different prime numbers. Well, okay. So yeah, well, before proving this, let me explain how you use this criterion to check that, to find a generator. Well, you just randomly guess an element that you assume is a generator, and then rise this element to these 2 powers and check that the resulting element is not 1. So basically here you have G to the power 12 and G to the power of 8. So you just want to check that in both cases you will get an non-identity element. Well, and here you have a lot of guessing, so you have to choose wisely. Well, there is no wise way to choose, you just guess. And the best way to guess is to go through elements of the form x minus x plus 1, x plus 2, x plus 3, x plus 4. Just go through all the linear elements with coefficient 1 here. And in this particular field, all the representatives are of the form a plus b times x. So believe me, if you take b to be 1 and go through all elements of the field z5 here as the free coefficient, you will finally get the generator. So I believe something like x plus 4, which is x minus 1, must give you a generator of this field. I just don't remember the exact answer, but here, this is the unpleasant part of this work. You have to guess, and if you guess early, oh, x plus 1, okay. Okay, we may compute it right now, it's not a problem. So, but in general, this is how you do it. There is no good way of finding a generator. You just guess and check if it's a generator, guess and check, guess and check, and finally, well, you have finitely many elements in the field. So finally, you will find the generator. But you should start from these simpler options, like from the linear polynomial. And if you cannot find a generator among linear polynomials, you switch to square polynomials, or if you have them in your field, etc., etc. So this is the main algorithm. But now I should probably prove why this happens. Yep.
Okay.
But just in case, are there any questions right now? Okay. Well, okay. Well, if let me show this from the left to right. If the order is 24, then, well, definitely in both cases you won't get 1, because if you have 1 here, the order is not greater than 12. There is a divisor of 12, and if you have 1 here, the order is the divisor of 8. Okay, so the left to right implication is clear. The interesting one is the right to left. Okay. Well, suppose that the contrary holds, that the order of the element G is smaller than 24. Then the order of G divides 24, which means that 24 equals the order of G times some number T. But then T must contain a prime divisor of 24. Well, T is some divisor of 24. Since 24 is divisible by 2 and 3, then T is a product of some power of 2 and some power of 3. But at least 2 divides T or 3 divides T. Let's assume for a moment that the first option holds. But then it means that T can be presented in the form 2 times T prime, and then you can divide by 2, and then you get 12. Well, let's rewrite it like this. Then you will get the order of G is equal to 24 over 2 times T prime. Okay. And this simply means that if you rise, this simply means that if you rise G to the power 24 over 2 times T prime, you will get 1, because this is just by definition of the order. This is the power that makes your element to be an identity. But then if you rise it again to the power of T prime, you will still get the element 1. But after rising to the power of T prime, you will get G to the power 24 over 2. And here is the contradiction with the fact that G to the power 24 over 2 is not 1. So this contradiction appears because we assume that the order is strictly smaller than 24, and there is some additional T in this expression. So because of this contradiction, we see that the order must be 24 exactly. I mean, I'm not sure that the explanation was totally clear. So if you have any questions or you want me to repeat the proof, I'll do it. Just tell me. Are there any questions regarding the proof from the right to left? Okay, so I assume it's clear. So now, should I check these conditions for the element x plus 1? Do you need me to do this?
Yes, because it's not quite clear how to put it in such power, like.
Okay, I'll show you the tricks. So, but before doing the computation, let me recall the construction of the field F25. So we constructed the F25 as Z5x over x squared plus 2. Okay, and now let's check the element G x plus 1. And what should we check? We should check that its 12th power is not 1 and that its 8th power is not 1. Okay, but here we use several tricks. First of all, if you rise to a power of 5, rising to the power of 5 is a homomorphism. So if you rise G to the power of 5, you will get x to the power of 5 plus 1 to the power of 5, which is x to the power of 5 plus 1. That's one trick you should use. The second trick you should use, well, by definition here, the expression x squared plus 2 is 0. So we know that x squared plus 2 is 0 in F25. So we know that the second power of x is minus 2. Okay?
Could you please explain why G in the 5th power, no, the previous one is x plus 1?
Okay. This is because we have this Frobenius automorphism. So if you have a field of characteristic, well, let's say we have a finite field of with p to the n elements, we may produce a map which takes x to the power of p. Okay, then this map is actually an isomorphism of fields. Well, it means that it preserves addition, multiplication, and takes 1-to-1. Okay? Well, so again, it preserves addition, it preserves multiplication, and takes 1-to-1. Well, the second and the third one are clear. Okay? Because, well, 1 goes to 1 to the power of p, which is 1, and if you take x times y, it goes to xy to the power of p, and this is exactly the same as x to the power of p and y to the power of p. So these two are clear. If not, just tell me. I will write the computation. So the interesting one is to check if it preserves the sum. So we want to show that x plus y to the power of p equals x to the power of p plus y to the power of p. So this is what we should prove. Well, how to do this? It's clear, it's simple. You just compute this expression directly. You know exactly all the summands here. It will be x to the p plus p over 1, x to the p minus 1, y, plus p over 2, x to the p minus 2, y squared, plus etc. And so on. And in the end, you will get something like this. And plus y to the p. Okay? So we have the required summands here, and we have some redundant summands. We want to avoid that. We want to show that all the red summands are 0. In order to do this, we need to show that pi divides p over k, where k is strictly greater than 0 and strictly smaller than pi. Well, suppose that we have proven this. This is just some fact about numbers, natural numbers. Suppose that we know this. How to prove using this that all the red guys are equal to 0? Well, in order to do this, we need to show that pi times z is equal to 0 in the field f pi to the n. Well, but this is clear because by definition, what is this? This is pi times 1 times z. Because multiplying by 1 doesn't change anything, but by definition of the characteristic, the first product is 0, hence the whole expression is 0. So pi times z is 0 for any z. Or if you wish, pi times z equals z plus z pi times. And well, again, so you just see that this is exactly the same thing as this expression, because here you just have 1 plus 1, and this expression is just 1 plus 1 pi times, and you multiply it by z, and because of this equality, you can open the brackets, and then you will get 1 times z pi times, and this is exactly the sum of z pi times. And this expression is this one by definition. So this is how you prove that this expression equals to this one, is equal to this one. And now, how do you apply this problem here? Well, for example, pi over 1, so you take this pi over 1, x to the pi minus 1, y. Then it equals pi times some number, let's say q, x to the pi minus 1, y. Well, why? Because since this guy is divisible by pi, it can be presented as pi times q. But now you take this to be z, well, and this is your pi. And then just apply this observation, and the result is 0. So this is how it's done. So all the summands here are 0. Just in case, are there any questions regarding this? Should I repeat this? Is it clear? So I didn't prove that this fact, but modular this fact, I was trying to explain how to prove that all the red summands are 0.
I think that's pretty obvious.
Oh, okay. Oh, but then you should have stopped me and tell me that, okay, it's clear, so don't waste our time, showing that. Okay, but is it clear why pi divides pi over k? Should I prove this?
Oh, no, it's clear.
Oh, it's clear. Okay. So now it's clear why we have this equality, yeah?
Yes.
Okay. Just don't hesitate to interrupt me. I mean, if something that I'm explaining is clear and obvious, just stop. Oh, kind of stupid question. Why pi times z equals 0? No, this is what we want to prove. Why pi z equals 0? Well, the first equality is pi z equals pi times 1 times z, because I can put the element 1 here between pi and z and put the brackets like this. But then pi times 1 equals 0 because of the definition of the characteristic, because by the definition of the characteristic is the smallest possible number pi, such that pi times 1 equals 0. Because by definition pi times 1 is just 1 plus 1 plus 1 pi times. So this is because of the characteristic. The characteristic of the field is equal to p, pi. Andrew, does it answer the question? Okay, that's good. Okay, so these are the tricks you should use. First of all, if you have a field of characteristic 5, then rising to the power of 5 is an isomorphism. So you can, it preserves addition and multiplication. So this is one of the tricks. And the second trick, you just look at the equation, and this equation, at the polynomial, and this polynomial is always 0 in the quotient, just by definition of the quotient. We just make this to be 0 in this quotient. So this is how the multiplication defined in this ring, first of all. So x squared plus 2 is 0 here, and you have this x squared equals minus 2. Well, and now you just need a couple of tricks to go to the 8th and 12th power as quick as possible. Well, for example, let's go to the power to the 8th power. So you take x squared is minus 2. Then just compute the 4th power is minus 2 square, which is 4, and this is minus 1, and this is minus 1. Oh, by the way, oh no, that's not what I'm sorry, I'm doing the wrong thing. We need, our element is x plus 1. So let me go here. So we take element x plus 1, and we should compute its 8th power. Well, how would I do this? Well, first I would compute its 5th power. Then it will be x to the 5 plus 1. And when I compute 5th power of x, it's the 4th power of x times x. The 2nd power of x is minus 2, and the 4th power of x is minus 2 to the 2, which is 4, which is minus 1. So this is minus 1. So this is just minus x. So the 5th power of x is minus x. So here we have 1 minus x. This is just the 5th power of x. Now, I've done it very quickly, but just in case. Can you follow? Is it clear?
Yes, yes.
Okay, and now in order to get the 8th power, I just need to multiply by the 3rd power. So x plus 1, 5th power, x plus 1, 3rd power. Well, here, what I would do, I would use that it x 1 minus x, 1 minus 1 plus x, and 1 plus x square. And then this is 1 minus x square, 1 plus x square. Again, x square is minus 2. So here I have 1 minus minus 2, which is 3. So this is 3 times 1 plus x square. Okay, and here, well, I have to open the brackets directly. This is 3 times 1 plus 2x plus x square. And again, x square is just minus 2. So we have 3. And here we get minus 1 plus 2x. And we see that this is not 1 because we have x here with a non-zero coefficient. So x plus 1 to the power of 8 is not 1. So this is how we compute the second condition. Oh, well, now we have to compute g to the 12th. Well, again, how do we compute this? Well, g to the 12th, well, I would compute g to the 5 times g to the 5 times g to the 2. So g to the 5 we already have computed. So g to the 5 is 1 minus x. So here we have 1 minus x square. This is this pair. And then 1 plus x square is this guy. And again, we have 1 minus x square. And here we use that x square is minus 2. So here we have 3 square. And 3 times 3 is 9. And 9 modular 5 is minus 1. And we see that this is not 1. So these are the tricks that I would use to compute a power of any element. So I just combine this Frobenius automorphism with computation of small powers, which can be done directly. And also, I would use, I could also use the power, well, the 8th power in order to compute this one. Because you see, well, when I can compute the 8th power, I actually computed the 6th power, well, here. Well, I could simplify my computation because this product is actually x plus 1 to the 6th. And the result of this computation is here, and it's 3. So instead of doing all this, I could say that this is g to the 6th times g to the 6th, and 6 is the 6th power is 3, so this is 3 times 3, and the result is minus 1. Well, you have to be creative here. There are a lot of ways, but the main trick is to use the Frobenius automorphism because it commutes with addition and multiplication, so it's easy to raise to the 5th power in this field. So if we had a field of characteristic 3, then rising to the 3rd power would be simple. And also you just use this equation to lower the power of x. And that's it. Also, you can use the fast algorithm for raising to a power, like computing only the second, the square of each element. But I believe using Frobenius automorphism is much quicker. A computer cannot use it efficiently, but a human can. Just in case, are there any questions regarding these computations?
No.
Okay, I guess it should be clear. Then, are there any other questions?
I have another question, but again, if someone else wants to ask, maybe.
Well, if they want, if they wanted to ask, they would ask. So,
Oh, okay, it's again a problem from the homework. It's again finding formula for the isomorphism.
okay.
I've sent it to the chat.
Oh, okay, I see. Let me show you how it should be done. You have these ring, and you want to find an isomorphism. There are actually two different isomorphisms, and there was a typo where I wrote find the isomorphism, but it should be reformulated as find an isomorphism, because there are two different isomorphisms here. But anyway, how do you do this? Well, first of all, when you see a quotient ring like that, you know that you have a Chinese remainder theorem. In any situation, if you see a quotient like this, try to apply a Chinese remainder theorem. So in this case, x cubed minus 1 is equal to x minus 1 times x squared plus x plus 1. So this is a product of two coprime polynomials. This one and this one are coprime. So the Chinese remainder theorem for the polynomials tells you that this is isomorphic to Rx quotient by x squared plus x plus 1 times Rx quotient by x minus 1. So this is the first step. Now, and you have to write down the explicit formulas for these isomorphisms. So how does it work? Well, it works exactly in the same way as it works in the case of integers. So what do you have here? Here you have a polynomial of degree at most 2. So it has a form a plus bx plus cx squared. So this is an element of this ring. This is how you define this ring, the set of all polynomials of degree strictly smaller than 3. And then it goes to g modular x squared plus x plus 1, comma, g modular x minus 1. Okay? But just in case, what are the elements here? The elements here are linear polynomials, the polynomials of the form a plus bx. And the polynomials here are the polynomials of degree strictly smaller than 1. So here just coefficients, free terms lead the elements of the field R. So this is exactly R, just by definition. And what does this rule do? Well, if you take a polynomial modular x minus 1, it's exactly the same thing as taking the value of the polynomial g at point 1. Well, if you divide by x minus 1 with remainder, the remainder is the value of the point at the point 1. And if you divide with remainder here, well, it simply means that you should replace x squared by minus 1 minus x. So the remainder here is a plus bx plus c, and you replace x squared by minus 1 minus x. So at the end, you will get a minus c plus b minus c times x.
And why x squared is minus 1 minus x?
Oh, okay, because, well, first of all, you can divide with the remainder here, but when you divide by this, with the remainder by this polynomial, you simply replace x squared by minus tail of this polynomial. Well, it's exactly the same as the reduction algorithm, because in this ring, x squared plus x minus 1 is equal to 0. So you have x squared plus x plus 1 is equal to 0 in this ring. So x squared is equal to minus 1 minus x. or you can so this is y, or you can perform the division with remainder directly. So you have this cx squared plus bx plus a, and you want to divide it by x squared plus x plus 1. Let's do it explicitly. So here you multiply by c, so you have cx squared plus cx plus c, and now you subtract one from another one. Here you cancel the terms, and at the end you will get b minus cx plus a minus c. And you see, you subtract the tail multiplied by c. So exactly what happens here. You subtract, which means you have minus here, the tail, which is 1 plus x, multiplied by c. And you see the result of the remainder here that's computed directly by the definition is exactly the same as the remainder here I computed, assuming that x squared should be replaced by minus tail of this polynomial. Okay, is it clear now?
Yes, now, yes. Thank you.
Okay, so at the end, the rule is this. This polynomial goes to a pair, this one, and the value of g at point 1, which is a plus b plus c. So the Chinese remainder theorem gives you an isomorphism of this ring with this product, which takes this polynomial to this pair of polynomials here and here respectively, okay?
Okay.
Well, then, well, first of all, this gives you a map in one direction. If you want to find a map in the other direction, you need to apply the procedure we used for the Chinese remainder theorem with integers. So you need to find a polynomial going to the element 1, 0, and a polynomial going to 0, 1, and then you produce the inverse map. I'll explain how to do this in a minute, but just in case, what will be the next step? So you see, we want to show that this guy is isomorphic to this one, and we splitted this one into a product of this ring and this ring. This is already the field of real numbers. So the next step is to show an isomorphism between this guy and the ring of field of complex numbers.
Mhm.
So if we find on the second step an isomorphism with C times R, so and we'll write the formulas taking elements here to elements here, then the composition of this isomorphism with this isomorphism from left to right will give you formulas for an isomorphism from this ring to this ring. And if you write the composition for the inverse map from here to here, and then from here to here, that gives you formula for an isomorphism from this product to the initial ring on the left. So this is the global overview of how you solve the problem. Okay?
Okay.
So, I mean, in both cases, you want to compute the direct map and the inverse map. So, and here you want to compute the direct map and the inverse map. So here we computed the direct map for the first isomorphism. So let's try to compute the inverse map, okay? So in order to compute the inverse map, you want to find a polynomial, a pair of polynomials. So you want to find a polynomial h1, which goes to 1, 0, and a polynomial h2, which goes to 0, 1. Well, you may guess a polynomial of this kind, but there is also an algorithm based on the Euclidean division algorithm. Okay, so let's apply a general algorithm. We have two polynomials, x squared plus x plus 1 and x minus 1. So let's try, let's find its greatest common divisor and expand the greatest common divisor as a sum of these two polynomials. But first of all, you need to find a remainder of the higher one with the lower one. So this will be what? Let's divide with remainder. Well, you have to do all these computations. X minus 1. So first of all, you multiply it by x, you will get x squared minus x. You subtract you will get 2x plus 1. So you multiply it by 2, you get 2x minus 2, and you subtract, you will get 3. Okay, so now you see that if you multiply this by x plus 2, the remainder will be 3. Okay, so let's divide the whole expression by 3. Then we see that 1 over 3 x squared plus x plus 1 equals 1 over 3 x plus 2 x minus 1 plus 1. So this is your greatest common divisor. This is your first polynomial, and this is your second polynomial. Now, as you can see, the polynomial 1 over 3 times this polynomial is the one taking you to 0, 0, 1 element. So this is your H2. Okay, and minus this polynomial is your H1, because you want to move it to the left and move this one to the right, and this give you H1. Just in case, is it clear, or should I explain why this is H2 and this is minus H1?
Could you please explain?
Okay, you see, because of this equality, the left-hand side is equal to the right-hand side. So this defines you a polynomial. Let's denote this by H2. But now, let's compute the remainder of H2 modular this polynomial. Well, since it's divisible by this polynomial, the remainder with respect to x squared plus x plus 1 is 0, exactly what we need. From the other hand, this thing is equal to this thing, and the remainder of this thing with respect to x minus 1 is 1. So this polynomial gives you remainder 1 modular x minus 1, exactly what we needed. So this explains why the left-hand side is H2. Okay? Now it's clear, or it's still unclear?
Those 1 and 0 are what do they mean? Like,
okay. 1, the number 1, the polynomial. Okay. So let me go back here. So what? Let me rewrite the whole isomorphism below, because I think it's important to see everything in front of your eyes instead of it being hidden somewhere in the previous computation. So you have this. Let me move the blackboard out of x quotient by x minus 1. Okay, so what are the elements here? The elements here are polynomials a plus bx plus cx squared. What are the elements here? Are a plus bx, and the elements here just, let's say, c. Okay, I should probably use different letters, but alas, there is no hope for using different letters. There are so few letters in the world. So the elements here, they are of this form. The elements here, they are of this form, where a, b, and c are real numbers. Okay?
yes.
Well, now when I say 1, 0, I mean 1 plus 0x, comma 0. I mean the polynomial. Well, I consider 1 as a polynomial.
Oh.
And when I say 0, 1, I mean 0 plus 0x, 0, 1. So I consider 0 as a polynomial, and 1, okay, is a constant c here. Okay? So now, because of this, so I want to find, I want to find a polynomial of this form which goes to this element, and another polynomial of this form which goes to this element. But how do I find such a polynomial? In order to find a polynomial with the first property, I need to find a polynomial such that its remainder with respect to x squared plus x plus 1 is 1, well, exactly 1, and its remainder with respect to x minus 1 is 0. So it must be divisible by x minus 1, and its remainder with respect to this guy is 1. And if I want to find a polynomial going to 0, 1, it means that I want this to be divisible by x squared plus x plus 1, but its remainder with respect to x minus 1 is 1, okay? So H2 solves this problem, and H1 solves this problem. And here, if you take this to be H2, as you can see, it's divisible by x squared plus x plus 1 because, well, I mean, let's write primes here because these are different A, B, and C than these ones. These are some other ones. So, and we computed the map from left to right. It's given by these expressions. Well, you can solve the for A, B, and C here in order to find appropriate polynomial, but using the greatest common divisor and its presentation as a sum of the polynomials with some polynomial coefficients, you can solve it directly. So this polynomial gives the remainder 0, and since it equals to this polynomial, it gives the remainder 1 here. Well, now, is it clear how it works and what this means and why H2, well, given by this formula, gives you this pair of elements?
Could you like return, go up a bit and?
Yep.
So when we found the remainders, so where we say that G maps to G modulo x squared plus x plus y.
Yeah.
Isn't it like the isomorphism we're searching for, or not? Why we are doing something else?
Oh, okay. Let me explain what we're doing. So this map gives you an isomorphism from left to right. Okay. But I want to find the inverse map.
Oh, so we're looking for inverse. Okay.
Yeah. We're looking for the inverse map, and we're doing it in exactly the same way we did it in case of integers. So first of all, we want to find the images for these two particular elements, but now the images are polynomials. So they are not integers, they are polynomials. We just need to find two polynomials here, and then any pair. So if we find this H1 and H2, then in order to produce a map in the opposite direction here, we produce the map as follows. Let's write here. So then an arbitrary pair is just a pair of polynomials, let's say G1 of x and G2 of x. Well, of course, G1 is linear and G2 is just a constant, but then the map in the opposite direction is given by the formula H1 G1 plus H2 G2. This is how it works. So exactly the same rule as we applied in case of integers. Okay?
Mm-hmm.
Well, now let's try to write this explicitly. So I have already found H2, it's this expression, and H1 is minus this expression. So I claim that H2 here is 1/3 x squared plus x plus 1, and H1 is 1/3 x plus 2, 1 minus x. Well, and then I should use here a prime plus b prime x and c prime for these polynomials, and I just substitute everything in this formula, and I will get a map from the right-hand side to the left-hand side. But just in case, there are several questions to ask. The first question is why h2 is this expression. The next question, why h1 is this expression. And the third question is why do we map these elements here. And the fourth question is how to compute the image of these guys here. The first question, is it clear why h2 is this expression?
Because we found it.
Yeah, so so was it clear how we found it?
Yes.
Okay. Mhm.
But we wanted to find a common greatest divisor and we didn't, or did we?
Yeah, we actually did, because we found the greatest common divisor here. First of all, that was the computation. We divided x squared plus x plus 1 by x minus 1, and the remainder is 3.
So
And
3 is their greatest common divisor. No.
so
or-
3 is their greatest common divisor, but 3 is an invertible element. We can divide by 3. So the greatest common divisor is unique up to multiplying by an invertible element. So 3, 1, 5, square root of pi minus 2, doesn't matter. Every non-zero element of a field is the same greatest divisor as the 1. I mean, you just divide this 3 by 1, or by 3, and you'll get the second line. So this means that 1 is the greatest common divisor of this guy and this guy.
With 1/3, right? Already.
Yeah, you add 1/3 in each place.
So 1 is the greatest common divisor for 1/3 of those polynomials, right?
Well, no, it's the greatest common divisor of this polynomial. Let's use a different color. Of this polynomial and this polynomial. Because you can use 1/3. You can use 1/3 because this is just a polynomial and this is just a polynomial. The greatest common divisor it's not unique. It's unique up to multiplying by an invertible element. By element 3 and 1/3, they are just invertible elements. So I just use 1 because, well, it's more convenient to use a greatest common divisor with highest coefficient, which is just the constant term, being normalized. I just want to normalize my greatest common divisor in such a way that the highest coefficient is 1. So here, the greatest common divisor is 3. It's not normalized. I just want to normalize.
Okay.
It's like in case of integers, your greatest common divisor has two options. It's either n or minus n. But it's more convenient to use positive integers to represent greatest common divisor. Well, let me show you a simple example here below. Well, for example, you may take two polynomials, let's say x times x minus 1 and x times x plus 1. Well, it's clear that the greatest common divisor, is x. But let's say you write 2 here and 3 here. Well, again, you say that the greatest common divisor is x. But what if I use 2 here and 2 here also? Then, well, you can say that the greatest common divisor is 2x. But we deal with polynomials, let's say in qx, or r, it was r of x. Our polynomials live here. So the element 2 is invertible. So the greatest common divisor is, well, you can normalize your greatest common divisor and say that x is also a greatest common divisor for these two polynomials. Because multiplying by 2 doesn't change anything. It's an invertible element. So you just want to normalize it in such a way that the highest coefficient here is just 1. Because by definition, a greatest common divisor is any polynomial dividing these two, and that any other divisor divides the greatest common divisor. Because if you take x, then the polynomial 2x also divides x. Why? Because x is equal 1/2 times 2x. because 2 is invertible, this guy divides this one. So there is no difference between x and 2x for you.
Okay, okay, I understood. Thank you.
Cool. So yeah, it's just a psychological problem, because when you deal with integers, it's somehow clear that 3 is not invertible element, but here 3 is invertible element, so you can replace it. So the second thing is why h1 is equal to this element. So since we have this greatest common divisor 1 is expressible in this form, well, when you move it to the left, then minus this expression will play the role of h1. Should I explain this?
No, it's clear.
Okay, then good. And then you just substitute everything into this formula. Well, it's some honest work. So you just want to, now I'll just write it in the opposite direction. So you take a prime, b prime, x, c prime, and you map this into what? You multiply 1/3 x plus 2, 1 minus x by a prime plus b prime x, plus then you use h2, which is 1/3 x squared plus x plus 1 times c prime. Well, then you need to expand all the brackets, and at the end you will get some expression which is something plus something x plus something x squared, and this will give you the final formula for the inverse map. And the coefficients here, they will depend on a prime, b prime, and c prime. Okay?
Yes.
So let me recall what.
Could you
what
return,
we
please?
did.
I haven't wrote it down yet.
Oh, okay. No problem.
I'm writing everything.
No problem. Yeah, I'm sorry for this mess.
No, it's okay. Okay, thank you.
So what were we doing? So we were trying to compute the inverse map from this product to this ring, and this is done via this last formula. Okay, so now we know these two isomorphisms from left to right, and its inverse from right to left. Okay. The second step is to find these isomorphisms. So we need to find the isomorphism from left to right and isomorphism from right to left. Okay. And as you may guess, it works like this. It takes this one to this one, just the identity map, because it's clear that this factor is just R, because all the reminders are just numbers. And the rules to multiply and add them are exactly the same as the rules in the ring R. So this is exactly the same as R. So is it clear?
Yes.
Okay, now the second thing you should do is to find an isomorphism between these two guys. And then if we find an isomorphism and its inverse, then we can write the isomorphism between this ring and this one just coordinate-wise. So you just apply this isomorphism to this coordinate and map this coefficient to this coefficient. Okay? So the problem we need to solve now is this. We want to find an isomorphism between R of x, quotient by x squared plus x plus 1, and C. So we want to find this and the inverse isomorphism. And that's the only thing that's left. Okay? So now, how to find such an isomorphism? Well, I will move to the right because there is not enough time, space below. So let me repeat this again. So if you want to find a map from this guy to any other map, how do you do this? First, you do it in two steps. You solve for x in C. So you have to find a solution for this equation in C, in the field of complex numbers. Well, there are actually two possible solutions. There are two solutions, R1 and R2. I will write them explicitly later, but I believe you can do this because you just know how to solve quadratic equations in complex numbers. Then each root of this polynomial gives you an isomorphism from the a homomorphism from the left ring to the right one, and this this homomorphism will be an isomorphism. So let me show you how to produce a homomorphism from left to right using the first rule. So the homomorphism, well, an element in this ring, it's a polynomial of the form a plus bx, okay? And the map is just a substitution. You replace x with the root. So you map it to this expression. Or if you choose the second root, the map takes the expression to a plus b times r2. And r1 and r2 are some complex numbers, so the expression on the right is a complex number. It belongs to C. So, and you should choose one of these rules. So this is the first isomorphism, let's say phi 1, and this is the second isomorphism, which is phi 2. So this map will be a homomorphism from left to right, and it's actually an isomorphism. So why it's an isomorphism? But before explaining why, just I want to clarify that everything is clear here. I want to be sure that everything is clear here. So the steps: first, you solve for x in this equation here on the right-hand side. You choose any root of this polynomial, and the map from left to right is given by substituting x by the root. Are there any questions regarding this procedure?
No.
Okay, so now why this is an isomorphism? Again, since the left-hand side is the field, well, there are two possible ideals in this in the field. You have either zero ideal or the whole field is the second possible ideal. There are no other ideals. And since the kernel of a map must be an ideal, so you have two options. Either the kernel is zero or the kernel is the whole ring. But we can see that the kernel is not equal to the whole ring because, for example, a plus 0x goes to a plus 0r1, so element a goes to the element a. So you do not take everything to zero. If the kernel is equal to the whole ring, then everything goes to zero, but one doesn't go to zero, it goes to one, okay?
Okay.
So hence the kernel must be zero, and hence this is an injective map. But now this is a vector space over R of dimension 2, and this is a vector space over R of dimension 2, and you have an injective linear map between two spaces of the same dimension. Then it's automatically surjective.
Why are they of the same dimension?
Well, because you see, C has basis 1 and I. The dimension is 2, okay? This quotient, all its elements are of this form. So here you have basis 1 and x.
Oh, okay.
This is how it's done. But I assume that you will use the fact that this map is an isomorphism as given, because during my seminar I explained why such a map is an isomorphism, and I assume that all other seminars explain this fact. So this well, on a different example probably, but and as I remember, I explained this during the lecture, and at least the lecture notes, they contain a similar example explaining why such a quotient is isomorphic to the field C.
Yeah, it's clear.
Okay, and so now you just need to compute the root explicitly. So, well, actually, well, this will be, well, if you solve this equation, let me write down the complex plane, then the polynomial x squared, x cubed minus 1 has 3 roots. They are just 1, another root, cubic root of 1, and the third cubic root of 1. So there's xi and xi bar, and xi and xi bar. So I mean, you split this as x minus 1, x squared plus x plus 1. So 1 is the solution of the first factor. So xi and xi bar are the solutions of the second factor. And this is exactly the polynomial we want to find the roots of. So, and we know how to compute all the cubic roots in complex numbers. So this xi is actually cosine of 2 pi over 3 plus I sine of 2 pi over 3. Well, and xi bar is exactly the same, but with minus here instead of plus. And now you can compute explicitly these things, because here you have pi over 3. So it's 60 degrees. So its cosine is minus 1 over 2, because it looks into the negative side. And the sine is square root of 3 over 2. So another option is to take minus 1 over 2 minus I square root of 3 over 2. So hence, the map from the left to right is given by this expression. Well, and then you can combine the real and the imaginary part, and in the end you will get this rule. So this is how homomorphism from left to right works.
Is this only one of them?
Yeah, this is only the first one, corresponding to this rule. So if you want to find the second one, so here, let me write it like this. So the second isomorphism will be the same, but here you will have minus. So a plus bx goes to a minus b over 2 minus I b square root of 3 over 2. So this is the second isomorphism. This is a different one. You may use any of them. So I didn't want you to find all possible isomorphism. Just take any of them. It suits the purpose of the problem. And then you want to find an inverse map for this specific isomorphism. Well, in order to find the inverse map, well, you could solve this. Well, you see, your map takes a plus bx to element of this form. Now you want to take an element of the form, let's say u plus vi. You want to map in the opposite direction. But here you see that u is equal to this, and v is okay. I wanted to write it for the first one, but okay, let's do it for the second one. It doesn't matter. So you just simply solve for a and b. Here. Well, as you can see, b is just 2 over square root of 3 with minus and the v, and then you substitute b in the first and you will have minus you'll have this. So you substitute B into the first equation, and you will find that A and B must be of this form. So the inverse map is given by the formula U plus VI goes to what? U minus 1 over square root of 3V plus, sorry, minus 2 over square root of 3B, or not B, Vx. So this is how the inverse map works. You just explicitly solve for the inverse map, and this is the inverse map. Well, in the case of the second isomorphism. For the first isomorphism, it can be done similarly. So in this case, B will be just 2 over square root of 3V, and here you will get plus. So you will replace these two minuses by pluses, as is in case of the blue isomorphism. So in case of blue isomorphism, you will have plus here and plus here. Okay, so let me summarize what's going on here. So I explained how to find an isomorphism between this ring and the field of complex numbers, and how to compute its inverse. So now it solves the problem of finding this isomorphism between this product and this product. And then what you was asked to do is to find the isomorphism from this guy to this guy. You just compute the composition. You just apply one isomorphism and then the other one, and compute the isomorphism from left to right, and then you go into the opposite direction and apply one isomorphism, compute one inverse, and then the second inverse, and then you get the inverse for this initial problem. Okay, are there any questions here?
So the idea is, I understood it, but when we have the complex plane, why do we have P over 3? Where did it come from?
Again, what wasn't clear? How did I solve the
why do we have P over 3? Why is that so?
Oh, okay. When you find all cubic roots on the complex plane, you start with 1 and you divide this into 3 sectors with the same angle. The whole sector is 2p, so 1/3 is 2p, or 2 pi over 3. So each angle is 2 pi over 3, and this part, let me zoom a bit, and this part, how to find this part is the half of the plane, the angle is pi, and I subtract 2 pi over 3, and here I have pi over 3, so it's 60 degrees. So here you have 120 degrees, 120 degrees, 120 degrees. So if this is 120 degrees, this is 180 degrees, so the difference here is 60 degrees. And for a triangle with 60, well, here you have a triangle with 60 degrees angle, so you can compute its cosine and sine. The cosine is 1 over 2, and the sine is minus, and its sine is square root of 3 over 2. Just school geometry. I don't know. So was it clear what I did here, or should I repeat completely, or probably from the scratch?
But could we just solve the?
Yeah, you can solve this equation. Yeah, no doubt. But that's what came to my mind, like at first, because you see the initial polynomial was x cubed minus 1. So the solutions for this equation are just two primitive roots of order 3 from identity. It doesn't matter. So the way you solve this equation doesn't matter. You can solve it in the usual way.
Okay, I got it.
It was just the way to simplify the computation. I just didn't want to compute. I wanted to explain you how to see this immediately without any computation. But if you don't see this, no problem. just compute it directly. Use the method you're sure that's right. I mean, just use the way you're sure that works. If you don't sure that something works or you don't know how to do something, just use another method. Just choose probably not the optimal method, but just the one method you're sure that works. And that's it. It's always better to use a working solution instead of using some tricky one that you are not sure that it's the right one or it works or something like that.
Okay, thank you.
No problem. Okay, are there any other questions? Yeah, there are 11 of us. Only the toughest guys are here. The ones who really want to know all the mysteries of the universe. How to answer
I don't think that solving this equation is a great mystery of the universe.
42 is the answer.
No, you're wrong. 37.
37, why?
Because it's a prime number.
Mm-hmm. But do you know? But then I have a better question. But why 42 is not the answer? You explain why 47 is the answer, but why 42 is not the answer?
Because it's not primary number.
It's not prime number. Okay. I know a lot of people who disagree with you. Not about 42 not being prime, but about 42 not being the answer to all questions of the universe. Okay, Hitchcock Guides tells the opposite. Are there any questions?
I have no other questions, so.
Oh, so you have no questions. Well, that means that now you know everything. So nothing stands between you and the algebra. So that's good. Emil, do you have a question? I've seen your mic.
I don't have any questions.
Okay. Well, if there are no questions, then probably we can stop. So, I mean, the reason why I'm here is because of you. So if you have no questions, then there is no reason to be here.
Actually, will you like upload this video or not?
Oh, yeah, this, okay, yeah, this will be uploaded. I'll ask Naira, she will upload it, no problem.
I'm sorry, I have another question. It's about, I'm not ready with the questions about the last lecture, lecture number 9, actually, not the last one. But is it possible to write to you if I had any questions about that tomorrow?
Yeah. You can always, you could always, and you can, and you will be able to write to me, and you should write to me, like anytime you have a question, just write to me your question, no problem. Like your email, your Telegram, like any way of contacting.
Even during the control work.
Again? Pardon? Probably that was a good joke, and I missed it. That's a shame.
I said even during the control work we'll be able
to
even
write. During the test. Yeah, no, actually, but that was a good joke. Yeah, that was a really nice joke. I agree. But the purpose of the control of the test is to check what kind of questions you can ask without my help. So yeah.
Okay, thank you a lot. Thanks.
No problem, guys.
Thank you.
No problem. Okay. By the way, I will still be here on this stream because there are some other guys who wanted to ask other questions regarding like,
Maybe
or-
you can advise us to revise something before the control work. Maybe, I don't know. It's just an example.
again?
Maybe you can advise us some details to revise. For example, say that this exercise from this homework can be quite useful, or just revise this topic.
Okay. Okay. So let me summarize some milestones of the course. Well, there are several topics that I want you to know. First of all, cryptography. Well, this is more or less a gem of the first part of the course, and it's based on some properties of finite abelian groups. So I want you to know how to find primitive roots and how of a finite abelian group, and how to decrypt and encrypt the information. So there will be definitely a problem related to cryptography. So that's not even a question. Then I want you to know how to deal with finite fields. So I will probably use finite fields in order to decrypt and encrypt information. So instead of ZP star, let's say you can use some FP star or FP square star, etc. Well, that's the first thing. The next thing, so regarding the finite fields, so I want you to know how to deal with finite fields, how to make computation with finite fields, how to find generators. So this is exactly the kind of problems we discussed here today. And so I want you not to be afraid of the finite fields. And the last thing is Grobner basis. I want you to know how to find a Grobner basis for a particular system of polynomials, and then how to make a reduction, how to compute a remainder using the Grobner base. So these three topics are crucial. So you will definitely encounter a problem related to these three topics. So if you know how to do all this stuff, then you're in a good position. So you don't need to worry, because the purpose of the test is to check whether you know how to do the main, how to solve the main problems that this course was about. That's it.
Okay, thank you. And am I correct that the control work will take 3 hours?
Yeah. Well,
Okay.
Let me tell you a couple of words regarding the duration of the test. Well, there is a rule that I cannot make the test longer than 2 hours, 40 minutes. But if you need time to complete the test, then I usually prefer to extend the time limit. And my experience tells me that usually 3 hours is a much better timing than just 2 hours and 40 minutes. So if you don't want the test to be so long, we can change it to 2 hours, 40 minutes, as it should be done by rules. But if you need some extra time at the end, it's up to you to be there up to 3 hours. So,
great, thank you for that opportunity. That's a nice option, by the way.
Yeah, so I believe it's better to have options than to have just one strict opportunity to fail. Okay.
And also, I have a question. How many tasks will be at control work?
Well, I cannot answer to this question because I still don't know how many tasks you will have, because the tasks do not exist. I mean, I will try to invent them tomorrow. So it's mystery even to me, how many tasks and what are the tasks.
Okay, thank you.
And will the tasks be based on homeworks only or on the seminar tasks also?
Well, for me, there is no difference between the homework and the seminar tasks because, well, more or less they're the same. So we just prepare you for the homework during the seminar, and then you just solve the homework. So, I mean, it doesn't hurt if you look at the seminar's problems, but more or less they're exactly the same as the problems at homework.
Okay.
Any other questions? Okay, then, well, if there is no questions, then thank you for being here. I hope it was helpful. And I will switch to Russian because I want to continue. Well, I will stop recording here and I will switch to Russian and continue the consultation with other guys in Russian.
Okay, thank you a lot.
No problem, guys.
Thank you.
Thank you.
Bye.
Thank you.
Bye.
Bye.